Welcome back, and our next talk is going to be Algorithm Design for Tensor Units by Rezaul Chowdhury.
So, good morning. So, I'm Rezaul. So, I'll be talking about some results that we published 4 or 5 years back, and then we forgot about it. And so, this is a joint work with Francesco Silvestri and Flavio Vella. And in fact, Francesco was the main driving force behind this. Right? I got involved in this later when both of us were attending this Hawaii workshop on parallel algorithms and data structures. So Francesco should be giving this talk, but I'm here now. What? So right. So all this happened. So tensor core units and the things like whatever I will be talking about, all this happened because of these deep neural networks, right? They revolutionized computations in various fields, but the computation they themselves do is really expensive, right? So deep neural networks and the computations that they do is really expensive, and that is really basically what they do is a lot of matrix multiplications. So as a result, to improve this performance, there were, specialized hardware accelerators were developed, like Google's tensor processing units, NVIDIA's tensor cores, and all those, right? So these specialized hardware were developed just to perform one special operation really efficiently, and that is matrix multiplication, right? A small, right, fixed size matrix multiplication very efficiently. So we'll call those tensor core units in general, right? Okay. So but the question then, like GPUs, in case of GPUs, which were developed for graphics and image processing, right? People later used them for general purpose computing. The question is, what about TCUs, these tensor core units? Are they just for DNNs, right? So they do their intended task really well, but can we use them for solving other problems? So that was the question that we were looking at. Okay. So so in order to do that, if you want to design algorithms for TCUs, it will be better if we have a computational model for this, right? If we a formal model that we can reason about when we design these algorithms. Okay. So our goal was to adapt fundamental algorithms to exploit these hardware accelerators that natively support small matrix multiplications, and we wanted to move beyond the domain of deep learning. Okay, deep neural networks. So that was the goal. Then our contribution is this: a new computational model, which we call TCU model, and this is a very simple and abstract framework, right, for designing algorithms that take advantage of TCUs. And I will talk about this later, right? It has weaknesses. And that's one of the main reasons why, right, after 4 or 5 years, I'm here to give this talk, because it has its limitations and their work needs to be done, right, to improve those. So, and we show that there is a variety of classic algorithms that we reframe in terms of small matrix multiplication, and we show that you can achieve really some speed up. Okay, and also we consider algorithms from a variety of problem areas, right? Like dense and sparse matrix operations, graph algorithms, signal processing, scientific computing, like stencil computations, right? And graph algorithms, as I said, all the shortest paths, not paths, shortest distances. It should be shortest distances. Okay, so those are our contributions. So now, if we want to design a computational model for TCUs, first let's try to figure out what we really need to capture, right, from general purpose from all the TCUs that we have. So the first thing is that we need to keep in mind that it has this hardware accelerated matrix multiplication, right? Usually they use these systolic array algorithms, right, that can multiply to square root of m by square root of m matrices in O of m time. But that doesn't mean that they improve the work. Work is still theta m to the power 3 over 2, right? Just that it's parallel time on that hardware. Then there is this latency cost, right? So you need to account for this cost for setting up the hardware or activating this unit. Particularly, it can be expensive if the unit is not connected to the CPU, right, through internal bus, right? And then there is this asymmetric behavior. Then when you are multiplying these matrices, these units often have this right matrix that has some fixed square size, and this left matrix that can be tall. Okay, so those are the things that we take into account. So yes, go ahead.
When you say matrix multiplication, is this just multiplication with like addition and multiplication?
Yes,
or
that's
is
it.
This, could you
No,
actually use different operations on the TCU?
No, just multiplication and accumulate, right? So that's it. It's not like min plus that we can use for shortest distances.
You're saying we cannot do min plus?
Right, that's what our model assumes, that you have just this. Multiply and accumulate, that's it. Okay, so now we have this MLTCU model. So this is really just the standard RAM model extended with a tensor unit. That the CPU has access to a tensor unit, right? That's it. Single CPU, one of the major limitations, with the tensor unit connected to it. Okay, and unlike RAM model, we have two parameters, M and L. So what they mean will become clear later. So primitive operation is multiply this mult AB, two matrices A and B, and put the result in C. So A is this is the left matrix, that is n times square root of M matrix, and the right matrix is a square matrix, square root of M by square root of M. I'm really sorry that you cannot really see other stuff. I can see here. So there are two. Anyways. So, and the right matrix is the square root of M by square root of M, and it computes this C equals C plus A times B in O of n times the square root of M plus L time. Here, n, which is at least square root of M, is the only parameter given by the algorithm itself. Okay. And the cost model is that the running time of an algorithm for this model, right, is the total time required for all CPU operations, including all calls to tensor units. Okay. And we also assume that there is no concurrency between CPU and the tensor unit. That means at most one of them will be executing, right, at any given time. Is that clear? So this is the model. Any question about this? Okay. So now, most of the algorithms here you will see that we'll do only simple adaptations, right, of existing algorithms, and we'll adapt them, and that's how we'll get some speed up. So the first one is large dense matrix multiplication. See, right? This is, many of these are really obvious. Okay, but still, let's go over them. Say, for example, instead of a square root of M by square root of M matrices, what if you have a square root of N by square root of N matrices, right, where N is far larger than M? Then what you can do, you can split matrix A into strips of length square root of N by square root of M, and B into submatrices of square root of M by square root of M, like this, right? Vertical strips, right? And these are all small square matrices of size square root of M by square root of M. And then what you do, you make N over M calls to the tensor unit to multiply. See this one. This strip with this one, that will update this column, right? And then next one is this, right? So you're multiplying that one. This is updating this column, that one, updating this column, like that. So that's, as straightforward as that. And if you just combine all this, the total complexity will turn out to be just N over M times cost of a single multiplication, right, of a tall matrix square root of N by square root of M by a square matrix square root of M by square root of M, and then this is the cost, N over M times O of this, and it turns out to be N to the power 3 over 2 divided by square root of M plus N over M times L. So as you can see, the speed up is really in square root of M. So this is the speed up that you get.
What was L again?
Which one? This.
What is L? What is the parameter L?
L is the latency, that activation time, right? And M is the matrix, size of the matrix, right matrix in the hardware, which is the square root of M by square root of M. Right? There are two matrices.
Square root of M comes from the TCU. It's a
right.
feature of
Yes, the hardware
TCU
itself.
hardware.
Right. Right. So this is large dense matrix multiplication. Yes, go ahead.
Question. I think in your model you are assuming a tall skinny matrix times a square matrix. Why is that tall skinny one?
So that is, I mean,
Or it's equivalent.
so that's often what happens in hardware, right? I mean, that's how they have it usually, right? You have this, what happens is they say, for example, in Google's TPU, I mean, at the time when we did this, they had this right matrix was 256 by 256, and the left matrix could be as tall as 96K times 256.
Can it be a wide stuff, or it's not a good idea?
No, it cannot be wide because the right matrix,
I see. Okay.
right? Okay. So, but what about fast dense matrix multiplication? So fast dense matrix, let's assume that we have a Strassen-like algorithm, right? That that has its recursive structure and takes time O of n to the power omega over 2, where omega is between 2 and 3, right? So, and in that case, what happens is this is a recursive algorithm. So recursively, the problem is being subdivided into smaller and smaller submatrices. At some point, you will reach a submatrix that is small enough that you can execute that, right, that product on the TCU, right? So that if that is square root of m by square root of m is the base case, then we will execute that on the TCU, and the trivial bound is simply this, that our runtime will be n to the power omega over 2 divided by m to the power omega over 2 minus 1 times this, right? So this is the speed up. But then again, what happens is, depending on L and M, relative value of L and M, you can do better than this. Okay, what you can do, instead of going to a base case of psi square root of m by square root of m, what you can do, you can stop at some p by p if L over m is, this ratio is larger than 3 minus omega divided by 2 minus omega, right? If that is larger than that, then you can stop at p by p, where p is this, right? And that will give you this complexity. Looks weird, right, and complicated, but this is really smaller than that, right? You can show that this will always be smaller than that, provided that holds. Is it clear? Right. So that's fast dense matrix multiplication. So, and several other TCU algorithms. I think I won't be talking about those here, but I will talk about other algorithms later. The first one is, say, Gaussian elimination without pivoting on a system of n linear equations, right? What you can do, you can recursively reduce it to matrix multiplications of a small size, right? And then, like Strassen's matrix multiplication, right? At the base case, you use this TCU, and as a result, you get this running time. Again, the speed up factor is square root of m here. So similarly, you can do transitive closure of an n-vertex graph. You get the same complexity. Okay, and all pair shortest distances. See, you can do all pair shortest distances using matrix multiplication type computation if you do min plus, right? But we do not support min plus. Okay, so that's why we cannot do the standard repeated squaring algorithm, right? That computes all pair shortest distances, right? Log n time repeated squaring. We cannot use that. But there is another algorithm, right? Seidel's algorithm for unweighted, undirected graphs. We can use that. Okay, so that uses standard matrix multiplication, and the complexity for the standard matrix multiplication, if you use Strassen-like algorithm, then the complexity will be something like this, right? Okay, again, you have some improvement here. Then integer multiplication as well, right? For integer multiplication, what happens is it is really like you really reduce it to somewhat like polynomial evaluation, right? You want to evaluate you write them as polynomials, product of integers as product of polynomials, and then what you do, you want to do batch polynomial evaluation, right, using matrix multiplication. That's where you can use matrix multiplication for that. And we can show that, in fact, you can improve Karatsuba's algorithm doing that, right? And the improvement will be this. Here, this tau is the word size, right? So we are multiplying two n-bit matrices, so n-bit integers, right? And tau is the word size that also appears in the complexity. And finally, batch polynomial evaluation that I was talking about. If you want to evaluate a polynomial of degree bound n at p different points, then the complexity turns out to be this, right? So I'll not be talking about this, but I mean, I can talk about this later if you are interested. Okay, so these are some of the algorithms. Then I will talk about other algorithms later. Any question about this? Okay, so what I'll be talking about now is that how do you do discrete Fourier transforms, right, using these matrix tensor core units, and then how do you use discrete Fourier transforms to improve running time of stencil computations, which appear often in scientific computing. So for discrete Fourier transform, so it is, right, as I was saying, it is widely used in image and signal processing and scientific computing. So what happens is you are given a vector x, right, and then you want to compute a discrete Fourier transform vector y. You see what that really means, right? So like this, you have this vector, right, x. There are endpoints here, right? You multiply that vector with this van der Waals matrix, right? As you can see, this van der Waals matrix it has a nice structure, as you can see. Okay, and if this is of length n, the vector, this van der Waals matrix will use this omega n. These omega n's, each of this is it is e to the power 2 pi I divided by n, which is cosine of 2 pi n times I plus I times sine of 2 pi n. It is the primitive nth root of unity. This is a complex number, right? That's fine. So I is, as you can see, square root of -1. So what happens is basically what you do, you take this matrix, it's a square matrix, and you multiply this vector, right, and this matrix, and you end up getting another vector. That is your DFT, right? So that is really, if you think about it closely, it is really evaluating, right, a polynomial written, right, as these values as coefficients, a polynomial of degree bound n, written these values as the coefficient, and evaluating that polynomial at each of the nth roots of unity, right? And those are the values. So these are values obtained by evaluating a polynomial written using these as the coefficients, degree bound n, and evaluating that polynomial at each of the nth roots of unity. So that's what it is really, right? But you may think, okay, this is a square matrix, n by n, right? Just reading this matrix will take n squared time, right? But as you can see, that's really what that doesn't happen, because this has a nice structure, right? So you do not need n square entries to describe this matrix. Okay, so this is what happens is this is a circulant, right, matrix. You can diagonalize it, and then you can really use just theta n space for representing this, and the algorithm, standard algorithm that you have for doing this evaluation is just theta n log n. We'll talk about that on the next slide, right? So that is that first Fourier transform algorithm given by Cooley-Tukey a long time back, right, in 60s or something like that, right? So what happens is that what you do, so you have this vector, right? So what you do, you write the vector also as a matrix, right? It will be an R times C matrix. Entire vector will be written in row measure order, right, in this matrix, right? You have this, so R times C matrix, you take that, it's transform this, sorry, C times R matrix, you take it transpose, it is R times C, and then what you do, you take the FFT of each of its rows recursively, right? So each of these rows is smaller than the original vector, right? So you take the FFT of the top row, then next second row, right? All those and CFFT, not C, RFFTs you take from there, right? Each of size C. Okay, then what you do, you multiply each of the entries by some Twiddle factors. Those are small complex numbers. You multiply them and you get this new matrix. And in this new matrix, you take each column and take the FFT of each column recursively, right? And you end up with this, right? And this, you read it off in the, you need to take its transpose. Okay, anyways, so but this is really your y vector if you write it down, right? In column measure order, row, yes, column measure order, so you need to take the transpose then to row measure, right? So this is your DFT. Okay, so now what I was saying is that if you set R and C both to square root of n, that means you have if you write this matrix as a square root of n by square root of n matrix, right, and do all the DFTs recursively, then the running time will be n log n. So that is standard Cooley-Tukey algorithm, right? Fast Fourier transform algorithm that everyone knows about. Now the question is, how do you do? What do you do on a TCU, right? If you want to run this algorithm on a TCU. So what we do is that, see, it has two steps where you take the FFT recursively, right? What we do is that we set our number of rows in this transpose matrix to be square root of m, and number of columns to be n over square root of m. Okay, so that's what we do here, right? So then this is then square root of m, n over square root of m, right? And then this step of taking DFTs recursively, okay, what you can do, you have a square root of m DFTs here that you want to compute on n over square root of m, I mean vectors of length n over square root of m, right? You do that recursively. Make sense, right? But the next step, when you are doing the column thing, right? Here, see, you have to take n over square root of m DFTs, but each of size is square root of m, right? If you have to take a DFT of a square root of m, then think about the van der Waals matrix. That will be square root of m by square root of m, right? Okay, that is not optimal, right? But you can fit it inside your hardware, right? Then what you do, you simply do this naive matrix multiplication, right? With that, right? So, and you end up getting n over L time to do this. So all these n over square root of m, right? DFTs. What you do, you have this van der Waals matrix, square root of m, square root of m. That is your right matrix, and the left matrix will be of length n over square root of m, right? And each row will correspond to a a vector of size square root of m. So that is the tall matrix, and the right side is the square matrix that you have. And if you do that, then it will take n plus L time. And if you put everything together, this is the recurrence. T of n is equal to square root of m times T of n over square root of m plus O of n plus L, right? And then it will turn out to be n times L over m plus log n to the base m. So here, log n to the base m, as you can see, m appears in the base of the log. That is your speed up. Does that make sense, right? Okay. So, I mean, the thing is this, you cannot expect to get a lot of speed up here, right? Because we are considering a single CPU, right? Augmented with the single TCU, right? And the input size itself is n, right? Okay, so this is FFT with a TCU. Okay, now, once we have that, see, multiplying two polynomials is now easy. Remember what I said about FFTs, that when you are taking an FFT of a vector, in fact, you are creating a polynomial of degree bound n in coefficient form and evaluating that polynomial at n different points, each of the point being one of the nth roots of unity, right? That is polynomial evaluation. Okay, so then what you can do is this, that you have these two polynomials that you want to multiply, each of degree bound n. Okay, so what you do, so these two polynomials are both in coefficient form. What you can do, you can take FFT of both. If you take FFT of both, then you are really evaluating each of the polynomials at n different points, right? That's what FFT does, right? At the roots of unity, right? So you evaluate polynomial A at n different roots and polynomial B at the same n different roots, right? You have these. So this is called the point value form of the polynomial, right? At point P naught, the value is A P naught. Point P1, value is A P1, like that. So what you do, from coefficient form, you go to point value form. Now you have both polynomials in point value form. But see, multiplying in point value form is really efficient, because you can now multiply in theta n time. Because if you want to multiply two polynomials in point value form, you simply multiply each of them. This times this times this. See, this is the product of these two polynomials in point value form, right? So that can be done in theta n time. And once you have that, what you can do inverse FFT. which is really like FFT, right? One can show that it is just in that van der Waals matrix, instead of omega n, you simply replace that with 1 over omega n and put 1 over n in front of everything. And the problem is the same, really, right? So you take inverse FFT, the cost is the same. So that transforms this product in point value, from point value form to coefficient form. That is your answer. Product of the two polynomials given in coefficient form, and the product itself is also in coefficient form. So this, again, takes time, right? Oh, where is it? N log n to the base m. To the base m, that is the speed up, right? The standard algorithm is n log n. Is it clear to everyone? Right? So we have this. We have polynomial multiplication in that time. Now what can we do about that, with that, right? What we can do, we can, am I out of time? 5 minutes? Okay. So I'll try to be quick somewhat. So what you can do is that stencil computations, these appear widely in scientific computation, right? So what happens is in stencil computation, what you are given, you are given a grid. It can be high dimensional. Let's talk about one dimensional grid here. So you have these input values of size n, right? And what you want to do, you want to apply a stencil, right? We will consider only linear stencils here. So what happens is if you have values in this row, what you can do, in order to compute this value, you take a linear combination of the values here, right? Some linear combination, right? The same linear combination everywhere. As a result, you will end up with values here. Then use that to end up with value, to calculate the values over there, right? You keep doing it, and for t time steps you do it. So that is, and then the output grid will be the values that you get after t time steps. That is your, right? Stencil. So this is a stencil computation, right? We're given an input grid of size n and t time steps, right? And as you can see, I'll skip over this, right? I'll come back to that maybe. It has many applications, and a standard algorithm will take theta and t and time, because size of the grid is n, you do it t steps, theta and t. That's your time, right? Okay. Now, what happens is, as I said, stencil computations can be bounded or unbounded. Let's only consider bounded. In case of bounded, what happens is, see, I was saying, if you want to compute this, you use these t values. The stencil can be larger. The weights can be different, right? I'm just talking about a very simple one, right? But what happens if you want to compute this value? You have these two values, that's right. But what happens with this? Where do you get this from? One option is to get it from here, wrap around, right? Okay, that is the periodic stencil computation, right? So another one is, if you want to compute this, you have these two, you do not have this, but maybe these values are given to you. These are boundary values, right? That is a periodic stencil. Make sense? If the values are given to you as boundary values, right, we'll call that a periodic. And if you wrap around, that is, we'll call that periodic. Okay, but remember the polynomial multiplication that we did using FFT? FFT by its nature, because it depends on the roots of unity, which are periodic, FFT itself is periodic, right? And what we can show is that, in fact, this periodic, I will not go into this, but you can show that if I give you an input grid, and if I give you a stencil, you can represent both the input grid and the stencil as polynomials in coefficient form, right? And then the stencil, let's skip over this because I do not have time. So what happens is, and the output will be just the product of those two polynomials. Polynomial computed from the input grid, right? Using the input values as the coefficients, right, of degree bound n, the polynomial will be. And from the stencil, you can also put the values of the stencil weights, right, as coefficients of another polynomial. You have got two polynomials, and if you multiply those two polynomials and restrict the grid size to n because of periodicity of FFT itself, you will end up getting a periodic output, right? Okay, that is applying one time step. Make sense? Now, but we are trying to apply t time steps, right? So this is the input grid polynomial, and this is the stencil polynomial. If you multiply this one and this one from a0 time step 0 to you go to time step 1. You multiply again, you go to time step 2, time step 3, time step like that, right? Time step t. There are these stencil polynomials appear t times, right? So, but these are product of polynomials, right? So this t, this is s to the power t. And these s to the power t can be computed using repeated squaring, using only log t polynomial multiplication, right? Okay, so we have that. But what we can do is now, if I give you input grid, stencil, evaluate it for t time steps. For these tensor core units, right? For standard CPUs, it's different. For tensor core units, we use this observation that stencils are often, they do not change, right? Your input grid will change. You will often apply the same stencil on different input grids, right? So let's assume that stencils are given to you ahead of time, and you can pre-process the stencil, right? And then whenever you are given an input grid, you use the pre-processed data to compute, right, the output grid. Okay, so the pre-processing, you take a stencil, convert it to a polynomial, take the FFT, right? So that gives you point value form of the polynomial. Do repeated squaring to compute s to the power t. That takes n log t time, right? Okay, so that is pre-processing, and you do that and you save it. And then now you have this input data, right? You have this initial data, take the FFT, it goes to point value form, right? And then you multiply this polynomial with this polynomial. We know that we can do that efficiently on TCU. And then you will get your output grid in point value form, do inverse FFT, and it will end up in coefficient form. And that is our output grid. And you can show that, I mean, clearly it will take n log n to the base m time, because we are excluding pre-processing, right? With pre-processing, you cannot get that improvement. Okay, now that you have how to know, oh, we're done? Okay, so I'll be done, right? So I'll skip over all these, a lot of stuff. I cannot cover this ever, right? I always have this, and I cannot go over this. I tried that in Darkstool. I couldn't. Anyways, so what happens is once you have this periodic grid, you can apply that as a subroutine on an aperiodic grid, right? And you get something like this in d-dimensional, right? Still, you have this improvement of log m, right, at the base. So that is that for stencils, and this TCU, as you have observed, that you have a speed up factor of square root of m or log m, something like that. That looks like, I mean, the speed up, I mean, the savings in I/O you get in external memory model, right? Indeed, one can show that if you have an I/O lower bound in external memory model, that will give you a lower bound on the running time in the TCU model, right? So that's about it. So what we did is that we have this TCU model, right? And we show that simple adaptations can give you speed up in theory, right? And we hope that this paves the way for broader adoptions of these accelerators in high-performance computing. But then there are open questions. We haven't implemented any of these, right? So what will be the empirical performance? We do not know. And there are a lot of other problems that you can try to speed up. And finally, the main weakness is that real accelerators really have multiple TCUs, right? And not only that, they also have vector units. Not only that, there are also precision stuff, right? So they support low precision arithmetic. We haven't accounted for any of those here, right? So that is the biggest open problem, right? But very recently, there is this paper that tries to address those, right? But they evaluated only, they analyzed only segmented operations, segmented sum and segmented scan, right? So there are all other problems that still you can try. So that's all I had to say. Thank you so much for your patience.
So just to make sure I understand this correctly, so the time you're spending is basically n log n, right, for an FFT?
N log n to the base m. So that is n log n divided by log m.
And this is done by TCU, which assumes unit time for a matrix multiplication of size square root of m.
No, it's not unit time. We are saying that the time is theta m, right? Work is m to the power 3/2, but time is not unit. Time is theta m, because it is systolic array implementation.
I see, okay.
Right? Okay.